Hello everyone, welcome back to my class series on chemistry for computer science and engineering stream under VCHES102 Technology University, module 1 part 3. This class series it include important points on a given topic of the module and discussing about mainly about revised Bloom's taxonomy level 3 as well as 4 question and their answers. So previous class videos I covered the initial part. This class I am covering the sensors for the measurement of dissolved oxygen. So in previous part, as per the comments that I received from the audience, so that I couldn't include some of the images. I thought that the images are available only the descriptive part I took, but I'm including that even the previous parts video that some of the images, important images, which are it will easy to understand that I understood that why they got the feedback like that. I'm including here in this part actually. It is a part of that part 2. Conductometric sensors, it was explained in my previous class video. So this is the schematic representation of a conductometric sensor, the inside that conductometric sensor. This is a conductometric electrode that we use. Okay. So here you can see this made up of two platinum plates. Two platinum plates. A conductometric sensor consists of two or more electrodes. Here we are using mainly platinum plates, which are conducting material such as metal or embedded in a non-conducting material, and it is embedded into glass or plastic. So it is connected, further connected to the glass or plastic. So when it is dipped into a solution, the solution are having positive and negative ions. By applying the voltage, they will be moving towards the respective electrodes, positive electrode, negative electrode, based on the number of electrons, number of charged particle present. We can measure the conductivity, or based on the ion nature, whether it is a smaller ion or bigger ion, so the size of the ion. Based on that also we can measure the conductivity, and we can see which type of ion is present, what is the reaction happened, or we can even check the end of a chemical reaction or any other conductometry related measurements can be done. This is the another one which is called as thermocouple. A schematic representation of thermocouple is given here in the image. Here two different type of metal wires are used, that is wire A and wire B, wire type A and wire type B, which is joined at a place which you call as hot junction, and they are also joined in another place which you call as joint cold junction. They again joined here actually, they connected it. Then it is took to the corresponding that voltage measuring device. So thermocouples are made up of two different type of metal wires that are joined at a point called the sensing junction. When there is a temperature difference, so here I kept a candle. Normal applications will take it to the atmosphere where based on the temperature difference between the sensing junction and the other junction. This is the sensing junction. This is the cold junction. Based on the temperature differences, it will measure what the temperature present in that. Next one, that is RTD, resistance temperature detector. They are typically made up of thin wire, often made up of platinum, which is wound into a coil and embedded in a ceramic or glass substrate. As the temperature of the wire changes, so does its electrical resistance. By measuring the resistance of the wire, the temperature can be determined using calibrated formula. So this is the simple schematic representation of a RTD. It consists of two lead wires, and there is a platinum wire coiled to a substrate, and this is the schematic representation of a resistant temperature RTDs. Then third one, that is thermistor. Thermistor, actually here three different thermistors image I got, so I presented here. They are temperature sensor which operate based on the principle of temperature dependence of resistance. The material made up the device is made up mainly of ceramic or polymer material. So this play part in the rod thermistor, the part which is either a ceramic or polymeric material, or the disc, it is a polymer or ceramic material, or bead, the end that bead, that is also a polymer or ceramic material which is doped with metal oxides such as nickel, copper or manganese, which will vary their resistance based on the temperature variation. This is photodiode. A photodiode consists of two semiconductors joined, N-type semiconductor and P-type semiconductor. When they join together, it becomes a PN junction. PN junction becomes a potential barrier. Potential barrier means electrons cannot uh, pass on both sides. Only when applied force is the electron can move only to one direction. That it cannot cross this. So whenever light falls on that PN junction, in that P and the N side, respective electrons as well as a Hall space will be generated, and those will be traveling through the external circuit to create the required current or voltage. Current is measured. Based on the current generated, we can see how much light is produced. Okay, so by measuring the availability of the current, you can see how much is the light present, or we are sensing the light. This is a photo transistor. A photo transistor, the images are given here. The schematic symbol is given in the first image, and some of the typical photo transistor which are available in the market, their images are also given. They work by using the incoming light to control the current flow through a device similar to a traditional transistor. So you may be knowing what is a transistor, how it works, the base emitter and that concept, collector emitter concept, it is there. Okay, so next, photo transistor, it got repeated. Okay, next, this particular task video topic, that is sensors for the measurement of dissolved oxygen, DO. You know what is dissolved oxygen? Dissolved oxygen, it is a molecular oxygen that we breathe. The same oxygen, if it is present in the liquids, along with the liquid, as dissolved in water, it is dissolved. That's why the aquatic animals, fishes, they can breathe. They are taking that oxygen. The aquatic plants, they are taking the dissolved oxygen. Okay, so dissolved oxygen, some amount of oxygen will be always in dissolved state in the water, that we have to measure in many of the times to check the quality of the water, or to use that water for some other purpose. So DO sensors are used to measure the amount of oxygen present in the liquid, which is critically in many industries, industrial, environmental and biological applications. One common type of dissolved oxygen sensor is the polarographic sensor, which operates based on the principles of electrochemistry. Electrochemistry principle you may be studied, or you may be seeing in your chemistry lab. So in a polarographic sensor, a cathode and an anode are placed in a liquid, and the voltage is applied to create a potential difference, schematically represented here. It has got mainly two electrodes, working electrode and a reference electrode. Okay, so your voltage, there is another one, counter electrode is there to minimize the error. Okay, so these are the two electrodes, and the water containing the dissolved oxygen we need to measure. So when we apply desired voltage, that is the dissociating voltage of oxygen. Okay, that particular voltage will make the oxygen to split into ions. So those oxygen will go to the cathode side, and it will be releasing the electrons. Okay, so that particular voltage, if it reduces it, how much oxygen is present, that much the reaction takes place, which can be measured by as a current. Okay, by giving voltage and measuring the current is directly proportional to the amount of oxygen present in that. That is the simple principle behind the polarographic sensor. Okay, so oxygen diffuses through a membrane, so that membrane I represented there, and current is proportional to amount of oxygen present, which is already given. Okay, so here given a membrane is given. In actual image it was not there, so I only put a square box here. So this is actually a cover to this electrode, which is actually oxygen permeable membrane. Okay, only oxygen can go through that, not other gas molecule or any other material will not mix with that oxygen and give erratic results, results with errors. Polar graphic sensor, the market what we see, it will not be schematic one, they are having of these shapes. So these are the different oxygen sensors available in the market. Okay, so its schematic one is represented in the previous image. Now another type of dissolved oxygen sensor, it is the optical sensor, which operate based on the principle of fluorescence. Okay, so the fluorescence based optical sensor schematic representation is given here. A fluorescent thin film is taken, which is the fluorescent which is responsible to oxygen, means it will change its color intensity based on the amount of oxygen present. Okay, and there are two LEDs used, one reference LED red source and one blue LED as a light source. It produces ultraviolet. When ultraviolet hits the fluorescent film, it will emit. So that is detected with the photo detector. So the emission on the fluorescent film, it will be based on the oxygen concentration present there. Varying oxygen concentration, different reflection light will be reflected in a different concentration. Based on that, the amount of oxygen can be detected. In this type of sensor, a fluorescent dye is excited by light, and the amount of oxygen present in the liquid affects the fluorescent intensity. Okay, so in this fluorescent dye excited light, the amount of oxygen present in the liquid, it affects the fluorescence intensity and it can be measured. So this changing fluorescence intensity can be used to determine the concentration of oxygen. Okay, so I'll continue. Okay, so it's the same image is given here. Now, DO sensors can also be classified based on their measurement range and accuracy. Some sensors are designed for low concentrations of oxygen, while others are measured high concentration of oxygen. The accuracy of the sensor can also vary depending on the design and calibration of the sensor. Okay, no more complications. One key consideration in the selection and use of a digital oxygen sensor is the type of membrane used. Okay, I said now already there is a membrane is kept in the first polarographic sensors. The type of membrane will affect the amount of dissolved oxygen, the content or the measurement will be affected. Different materials and thickness can impact the response time, sensitivity, and accuracy of the sensor. One challenge in use of dissolved oxygen sensor is the potential for interference from other gases or contaminants in the liquid, which can impact the accuracy and reliability of the measurement. So one of the challenges that we have is already given here. It can be addressed through careful calibration and selection of the sensor and its components. In addition, the temperature, the pressure, the liquid which we are measuring, the oxygen, all can impact the sensing or the sensibility of the sensor, and the sensors may need to be calibrated or compensated for changes in the variables. DO sensors are used in a wide range of applications, including aquaculture, wastewater treatment, brewing, and medical devices. Okay, so in each applications, the sensors may need to be customized or optimized for specific requirements and conditions. DO sensors are also used in research where they can provide insights into the dynamics of oxygen transport and consumption in biological systems, such as in cell culture or tissue engineering. Question: what are some of the key technical and design challenges in developing sensors for the measurement of dissolved oxygen, and how can these be addressed? I'll be reading this one because I already explained what is the main part of dissolved oxygen. So only giving what type of questions can be asked at level 3, and how we need to answer it. What are the expectation for this type of question? Level 3 question. Answer: developing sensor for the measurement of dissolved oxygen can be challenging as it requires addressing several key technical and design issues. One challenge is achieving a high accuracy and sensitivity, particularly in the presence of interference from other gases or contaminants other than oxygen. Other gases or contaminants also will be there, which can be addressed by optimizing the design of the sensor to minimize the background noise, such as through the use of advanced materials, signal processing techniques, or improved membrane design. Another challenge is achieving the reliable long-term performance and stability, particularly in harsh or corrosive environment, in which we have to continuously measure the dissolved oxygen content, which can be addressed carefully by selection of material, fabrication technique, as well as giving any protective coating or barrier layer to minimize corrosion and degradation over time. Fourth point, using the specialized material for fabrication techniques can increase the cost of the device and limits its usability or scalability. To address these issues, researchers are exploring alternative material and fabrication methods that can improve performances while maintaining cost effectiveness and scalability, such as the use of low cost scalable processes like inkjet printing or roll to roll processing. Okay, so by varying the techniques used to manufacture, it can be addressed. The development of a resolution sensor requires a multidisciplinary approach that combines expertise in material science, chemistry, electronics, and manufacturing, as well as a deep understanding of specific requirements of the application. Addressing these technical and design challenges can lead to development of sensor with improved accuracy, sensitivity, stability, and cost effectiveness, enabling a wide range of environmental, industrial, and biomedical applications. Second question, compare and contrast the principle of operation of polarographic and optical sensors for the measurement of dissolved oxygen and describe their advantages and disadvantages. So this is a RBT level 4 question. Therefore, the answer how it is answered, how it can be answered. Polarographic sensors and optical sensors are two type of sensor used for the measurement of dissolved oxygen. Okay, in polarographic sensor, the work is based on a principle of electrochemical reaction. That means electrodes, anode, cathode. That concept we call as electrochemical reaction, where oxygen is reduced at a cathode to produce a current, and the current it is proportional to how much oxygen is reduced at a cathode, which gives the amount of oxygen present in that. And we need to have a thin membrane to protect the cathode from sample solution and to promote oxygen diffusion at the cathode. On the other hand, the optical sensors rely on the quenching of fluorescence, that is fluorescence based or luminescence based oxygen optical sensors. These sensors use fluorophore or luminophore, the material which is usually called as the material which gives fluorescence we call it as fluorophore. Like that, the material which gives luminescence we call it as luminophore, which is this sensitivity should be sensitive to oxygen, so that when light falls on that, it will produce the it emits the light and we can color. Okay. uh, then optical sensors can be more robust and require less maintenance than polarographic sensors, but they can be more expensive and sensitive to interference from other substances. More robust means they are more fast, more accurate, and less maintenance is required. Polographic sensors have the advantages of being low cost, and they have a relatively high sensitivity to changes in oxygen concentration. They also have a long service life and are robust in harsh environments. However, they require regular maintenance, calibration to ensure the accuracy, and are sensitive to interference from other gases which can affect their accuracy. That about the polographic sensors. Whereas, in contrast, the optical sensors are generally more expensive than polarographic sensors, but they offer the advantages of being more stable, less sensitive to interferences from other gases. They are also generally easier to use and require less maintenance than polarographic sensors. However, they can be sensitive to temperature fluctuations and have shorter service life. In summary, both polographic and optical sensors have their advantages and disadvantages when it comes to measuring dissolved oxygen. The choice of sensor always depends upon the requirement, the specific requirement of the application, including the accuracy or sensitivity, robustness or cost or ease of use. Discuss the limitations and future directions of sensors for the measurement of dissolved oxygen in complex environment, such as in vivo measurements. In vivo measurements means which is something in human beings related measurements, live measurements. Level 4 question, little bit tricky question. Answer is given. Sensor for the measurement of dissolved oxygen have seen significant advances in recent years. However, several limitations still exist, which when it comes to their use in complex environments such as in vivo measurements. Okay, even though we do lab, we test it and we getting result, but in actual practice in complex environments like the in vivo, when it comes, it has several limitations. One limitation is the difficulty in ensuring the sensor is in a direct contact with the sample while avoiding the interference from other substances. Where we want to measure the sensor, we have to make sure that it is in contact with that area, and should not disturb the other substances. In case of in vivo measurements, it can be particularly challenged due to the complex and dynamic nature of the environment, which can include the cellular interaction, biofilms, and other structures that can interfere with the sensor's performance. Suppose in our blood, we want to measure the oxygen concentration in the blood. If we keep a device, the device may be distracted by other cells present near to that. Cellular interaction may be formed, or the our body will treat that device which is kept inside as a strange material. Therefore, they may form their own biofilms to protect it or to cover it, just like when we get a fever or when we get a cold, we are getting the cough is nothing but our body only creating some protein which covers that or control that virus or the pathogens. Okay, so like that biofilms possibilities are there which will affect the measurement. Another limitation is the impact of other physiological forces on factors on the measurement of disorders such as temperature, pressure, and pH. Because this it can affect the solubility of oxygen. Varying temperature or solubility of oxygen is different. Varying pressure, the solubility of oxygen is different. Different pH, the oxygen solubility is different. Therefore, this also has to be addressed. It requires careful calibration of the instrument, or we have to identify the components in such a way that as well as a deep knowledge about all these conditions, the temperature, pressure, pH knowledge. If it is there, then only we can tackle it. Despite these challenges, researchers are exploring new directions to improve the performances and reliability of sensors for the measurement of DO in complex environment. One promising approach is the use of micro and nano fabrication techniques to create sensors that are more robust, scalable, and easier to integrate with other systems. Additionally, researchers are exploring new materials and sensing strategies which can enhance the sensitivity and reduce interferences from other substances, such as the use of carbon-based material, metal organic frameworks, enzyme-based sensors are used. Another future direction is the integration of multiple sensing modalities to obtain a more complex, complete picture of the environment, such as combining DO measurement with the pH sensor, temperature sensor together, working together. This can provide a more comprehensive understanding of the environment and improve the accuracy of the measurements. Additionally, new techniques for data processing and machine learnings are being explored to extract more information from the sensors data and improve the interpretation and analysis of the results. Subscribe and support me. Subscribe to my YouTube channel and support me for my effort that I am taking. My YouTube channel is My Intuition 4865. Thank you once again.